So we've been talking a little bit about this idea of random assignment for experimental design. And the idea that I've sort of put forward has been that if you use random assignment to put people or cases or things that you're studying into two different groups, those groups will be basically the same and will be basically the same on every possible dimension. But I think it's worth maybe digging into what that means, basically the same, a little bit more. And there's a class project, either online or on campus, that will kind of test some of this, but I want to lay some theoretical groundwork for it. So if we think about random processes like flipping coins, and if you flip a coin 10 times, you might expect that you'll get 5 heads and 5 tails. That's roughly what should happen with a random coin. But it's not guaranteed. If I flip a coin 10 times, I might end up with 6 tails and 4 heads, right? And that can happen too. And so one of the things that we know about randomness is that it's not perfect. Sometimes we get results that are too high, and sometimes we get results that are too low, and that's okay. The process is still random. But if we increase the number of samples that we have, the number of, or I should say, cases in our samples, so instead of flipping a coin 10 times, I'm going to flip it 100 times or 1,000 times. If I flip it 1,000 times, getting 60% of that 1,000 to be tails is pretty unlikely. I might get a few more tails than heads, but probably not 600 to 400. That would be a more unusual kind of thing to happen. And so one thing that we also know about randomness is that our sample size get larger, those sort of weird bouncing around of samples and randomness tends to be less volatile. Our samples tend to be more reliable. And so when we're thinking about what it means for two groups to be similar, we need to understand that one, samples do bounce around, that random processes occasionally produce results that are too high or too low. And two, with larger samples, you will get less of that bouncing around, or the bouncing around will be less extreme on average. And so this sort of is something we're going to be working with over the course of the semester, but feeds into this idea of the sampling distribution. I want to very briefly run through the sampling distribution and what that is and kind of how it works. The sampling distribution is something that mathematicians have sort of developed. It's an abstract idea. This isn't a real thing. It doesn't exist out there, but it's the idea of what would happen if you could take a sample, record a value from that sample. So the, I don't know, average height of 1,000 people, and then take another sample of 1,000 people and record the average height, and another sample, and over and over and over until you've taken every single possible sample that could ever be taken of 1,000 people, measured their heights, and then you have all these results. And if we were to sort of plot those results, what we would find is that most of those samples are, one, correct. They would be centered around the true population value for all of the people out there, not just the ones that we've sampled, but overall samples give us correct results. Most of the results that aren't sort of smack dab correct would be pretty close. It'd be a little bit above, a little bit below. Sometimes that can happen in the extremes, but it's much less common. And so what we find is that samples in general follow this sort of idea of that we've observed when talking about other random processes, that sometimes you get results that are too high and sometimes you get results that are too low. And so when we talk about experimental design and samples being roughly equivalent, what we're saying is there's some bouncing around. Some will be too high, some will be too low, but they're going to generally fall pretty close to the center on that sampling distribution. They were unlikely to see sort of those extreme tail values, those sort of weird samples where everybody that we measured was over 6'3", right? That's really unlikely to happen, but not guaranteed. And so the way that we tend to define this is by looking at two standard deviations on the sampling distribution. It's sometimes called two standard errors. How off are your samples? And sort of use that as sort of a range in which we can say, yeah, I'm not really sure, where my particular sample is, but I'm pretty sure that my sample is pretty close to the center. And in the center, the true value is probably captured within this range of two standard errors. And so I think one way to think about this is if you're, sitting over on the dotted line, the first dotted line to the right on that little sort of bell-shaped curve, and that's where your particular sample landed. The true value is a little bit to your right, and if you were to reach out those distances of two standard deviations or two standard errors, that range, that zone, is going to capture some extreme values, but it's also going to capture the true population value. And so what we can say with our individual sample is it's probably within this range of the true population value of what we're interested in. And so if we have two samples that we've drawn, both exhibiting this randomness process, sometimes they're going to be too high, sometimes they're going to be too low. What we're essentially saying is if I have two samples and they both reach out those two standard deviations or two standard errors from the sampling distribution, there's going to be some overlap. That range is going to overlap, that they're not going to be so extremely different that, even with those two standard errors tacked on for confidence intervals, they're going to be just this divergent things that don't look at all alike. And so when we say these samples are similar with experimental randomization, what we're saying is that most of the time there's going to be that overlap. Now, I should say that overlap will be small, but I can't necessarily say that because it depends in part on how large your sample is. So I don't feel comfortable saying that the differences are going to be small, nor do I feel comfortable saying that the differences are always going to be overlapping, that there's always going to be that sort of that zone where those two samples match up with those confidence intervals, because occasionally we do draw samples that are really extreme, that are really bizarre, right? Where we draw a sample of 1,000 people and everybody in our sample is over 6'3". That can happen. And when that happens, even when we put our confidence intervals around those samples and say this is the range that we think we're working with, that range isn't necessarily going to overlap with another sample. And so what randomization does for us in an experimental sense is it says that on almost everything, there's going to be this overlap where they're going to be fairly similar on any dimension that you measure, but not always. Occasionally, weird things can happen. Now, what does occasionally mean? That's a good question. How frequently are we going to see these sort of weird situations where we actually do have real differences between our two randomized groups? Well, it depends on how far out you go with those confidence intervals. If we go out 2, which is the standard, that's going to catch 95% of all samples. And so basically 95% of the time, there's going to be overlap and we don't have to worry about it. But 5% of the time, we're going to have weird samples. 5% of the time, we're going to have samples that just don't behave. And I would suggest to you that about 5% of the time, actually, it's probably closer to 2.5% of the time, you can get samples that are so wacky and so weird with those two confidence intervals that it's going to stand out in a statistical sense, that we're not going to be able to say confidently that these things are similar. We can get around that by increasing our confidence intervals out. We can get around that by increasing our sample size. But nothing is perfect. There's always the possibility that there is some dimension where your samples are not actually similar. Now, there are two important caveats that maybe make that not such a big problem. One of those caveats is, what are the odds that the factor that is different, that didn't match up appropriately, is causally related to the thing that you're studying, right? And so if it's, people have, toes on their left feet that are slightly longer than toes on their right feet, I'm guessing that has almost no relationship to anything we're interested in the social sciences. And so even though it's different, maybe it's not a big deal. But if it's, I put all the men in one group and all the women in the other group, gender is related to a lot of things in the social sciences, and maybe that's a problem. And so not every difference is necessarily a point of concern. It's just the things that were potentially relevant. But again, that gets us in sort of a bind where we're trying to get out of the experimental randomization and trying to think theoretically about what's relevant and what's not. The second way to sort of resolve this limitation in experimental randomization, that you can get groups that are different on theoretically salient dimensions, that makes it difficult to say confidently that we've ruled out those other explanations because the groups are actually different in some important ways. The solution to that is replication. That if I draw two samples and they happen to be different, my gender distribution is too many men, not enough women in the two groups, it's unlikely that the next person who does this study, who does this replication process, is going to draw samples that have that same problem. They'll probably have other problems, differences in age or differences in height or differences in length of toes and left and right feet. Those differences might show up, but it's unlikely that they're going to get the same differences between their samples as I saw in mine. And so replication is a way to sort of sort out, did you draw weird samples that gave you results that, aren't reliable, or did you draw samples that, were a little bit weird, but that didn't really affect our findings and our conclusions? And replication is really the only way that we can get at that and overcome the limitations of experimental randomization. And this goes back to something that I've been trying to argue since the beginning of this whole discussion in this course, is that science is something that really has to exist within a community. That I, as an individual operating on my own, using an experimental design just once, I'm gonna have a really hard time drawing conclusions from that, because I can draw conclusions easily, but I can have a hard time drawing valid conclusions from it, because I don't know if my study suffered from one of these flaws of just, I drew wonky samples, and it just so happened that the dimension that was wonky was something that mattered. But if I'm participating in a community, other people can look at that and say, hey, that's an interesting study. I'm curious if that would hold up. I'll do it slightly differently. See if we get similar results or different results. I find different results, and we go back and have a conversation about whether my original results were flawed, whether someone else's results are flawed, if there was something different in how we set it up. And then we go and we try it again a third way to see if we can iron out those differences. And that's a really valuable process. And it's the process of science of, again we try it, and again we try it, and again we try it, that actually helps make this logic of experimental design actually work effectively, and helps us sort of iron over or paper over or patch over some of the quirky things that can and do happen with randomness.